work with this polynomial opener here. All right, so we're going to start. This is going to take a little bit of time to do, but it is going to get you there. Now, you know how to find a conjugate. What was the conjugate of this one? So, root 7 plus root 4. How do you multiply those together? Do what? What would the answer be for this when you multiply these together? Huh? 7 minus 4, which is 3. Remember, you're doing, in this case, a minus b times a plus b will give you a squared minus b squared. So you're taking the square of the square root of 7. So when I do that, I'm not taking the square root of 7 and I square it, it makes it go away. It's just 7. All right? The same thing here with 4, you do the same thing. So doing the square root of 7, I'm squaring it minus the square root of 4 squared, which would give me 4. So the answer is 3 there. So now when I'm rationalizing, remember, I'm trying to get rid of this square root symbols. Well, the method or the practice that we do is multiply by its conjugate. So we know what we get on the bottom, which is 3. On top, I'm going to get 2 root 7 plus 2 root 4. Anybody know what 2 root 4 is? That number is 4. Now, when I'm writing my rational numbers, my irrational numbers, it's a plus or minus the square root of b. So this is kind of written in the wrong direction. I need it to be written as 4 plus 2 root 7 all over 3. So I need to switch the positions. Okay? Now remember, this is equivalent to 4/3. So either one of these answers would be correct. All right? All right. We'll get better at that. We've got one every single day this week. Well, for the openers. I think I have 4 openers. I think we're having a quiz on Friday. So maybe. How many are there? Oh, sorry. There's 5 days.
No quiz this week?
No, we do have a quiz. Sometimes we do 2 a week. All right, now, we're not like Algebra 1 where you have it every Friday. Or geometry. All right, so take a look right here. Now, anytime we say find the roots, when we say find the roots, we also mean the word solve here. Anybody know another word for roots? Yeah, they are x-intercepts. What else are they? It's another word we use for roots. Zeros is correct. Thank you, Peyton. Anything else? 0, roots, and solutions. So when you solve something, you find solutions. Okay? So we have 4 different names for really the same number is what it comes out to. Just remember x-intercepts are kind of like zeros in this case. Intercepts and zeros are both written as ordered pairs most of the time. Sometimes zeros are written with an equal sign. Intercepts are always written with ordered pairs. All right, so in order to solve this, anybody got a plan for solving a, what is that? That is a name as polynomial. So we're looking at a polynomial here. Grouping. Aubrey says, hey, I've got 4 terms. Group the first 2, group the last 2. As I said, that the factoring would become a little bit easier. All right. You don't have the x's, y's, and z's in there. You don't have fractions. You don't have negative exponents. So what is common in the first 2? X squared. What does it leaves me? All right. So the second group here, right here also needs to have a 4x minus 3. And what number did you yank out of the second group right here? -1 is correct. Now we're going to do a super GCF. What are you yanking out now? All right, so Kevin says x minus 4x minus 3, leaving me x squared minus 1. What now? Ooh, I can factor it further. Don't forget your y equals 4x minus 3, and then x plus 1 and x minus 1. Don't forget your y equals or f of x equals. All right? Now we have it factored. When you are in factored form, now we are going to go to solve it. What method do we use to solve?
0.
Correct. We are going to do ZPP. So we're going to do the zero product property. All right? So when you do anything, and when I ask you to solve with a polynomial, you're going to go into what we call ZPP. In order to do ZPP, you always have to have factored form. Okay? The zero product property is you need to be thinking, when I do zero product property, I need factors. Okay? So you're just going to take 4x minus 3 set equal to 0, x plus 1 set equal to 0, and x minus 1 set equal to 0. Go ahead and solve each of those. So x is equal to 1. X is equal to -1. Add the 3. Divide by 4. So x is equal to 3/4. Your intercepts in this case will be 3 over 4 comma 0, -1 comma 0, and 1, 0. These are your x-intercepts. How many solutions did you end up with? All right. And I've talked about this fundamental theorem of algebra. Whatever your index is here is the number of solutions you'll have down here. That is the fundamental theorem of algebra. Now, sometimes they're not going to be real solutions. Okay? They will be imaginary. Sometimes they will repeat on the same spot multiple times. So you can have repeating. So if I have like an x to the 12th, you could have it only intersect maybe 2 times, and all the others could be imaginary. All right, so you could have 10 imaginary solutions. You could end up with none of them crossing on a x to the 12th. You could have 12 imaginary solutions, and you're like, what does that mean? Well, we'll talk about it later, all right? But in this case here, it just means it's not crossing x-axis. So sometimes they touch the x-axis, sometimes they don't. All right, we're dealing with a cubic. All right, it's going to intersect it 3 times in this particular problem. How do you find your y-intercept? All right, I like that. We're going to write down plug in 0 for x, and when you do that, and you're looking at standard form, it's always going to be that back number. So this one here is going to be 0, 3. I mean, think about it. If you look at this particular problem right here, and let me erase all of these so you can see right here. If you made these numbers right here, that's 0, and that is 0, and that is 0, and you do an f of 0, these would all disappear. The only thing you're going to be left with is that number 3. That's why it's 0, 3. Degree. Well, the degree is your highest power. So in this case here, it is a 3. So we actually have names for these. So if you have, this one's x cubed, we have x to the 4th, we have an x to the 5th, we have an x squared, we have an x, and then we have a number. All right, so anybody know what x to the 3rd power is called? Called cubic. Anybody know what x squared would be called? Ends with an ick. Quadratic. Anybody know what x would be? Y equals x is a what? It is linear. A linearic. Yeah. I know you. Quadratic is a picture of a parabola. All right. So you guys know what fourth one? The fourth one is what we call a quartic. It is a quarter. Okay. The last one is what we call a quintic. All right. Now, the reason when we became the United States, we separated from England. England actually had 5. They had pence. Pence would be 100 pence would make $1. 5 quid would make $1 as well. They had 20-cent pieces. We wanted to be different, so we went with 4 quarters. Okay, so we didn't want to be so similar. So we have 4 quarters equals $1. So it's quartic. So when you see x to the 4th is 7. Okay. Anything above that would just be called 6th degree or beyond, okay? You'll have to know these names. These are names that you need to know and be familiar with, okay?
Can you read that?
Yep. I'm not erasing that. So. These are all polynomials. They all fall underneath the polynomial name, okay? Poly means, anybody know what poly means? Yeah, it's just more, right? Poly, the word actually, the prefix is just more. All right, so we have a monomial. A monomial is just like 3x squared. There is no plus or minus sign separating them. If I put a plus 3, then that makes a binomial. All right, if I add an x and then a plus 1, that has 3 terms. That's called a trinomial. If I have more than that, it would be a polynomial. We actually call all of them in the category as polynomials, all the way from 10 terms or infinite number of terms all the way down, okay? Then we get very specific with trinomial, binomial, and monomial, and that's it. So it is just separating the number of terms. So when you see polynomial, it is really talking about number of terms. When we classify it by degree, it is the highest power it has, how many times it's going to hit the x-axis, or the x-plane, I guess is what I wouldn't say, not x-axis, but the plane of x, because you have imaginary numbers they hit there as well. All right, now, see graph, when we're graphing, and this is talking about graphing right here, we have what we call in behavior, right? The in behavior is what's happening at infinity. Now, there are only 2 places that we want to care about is how far to the right and how far left. A polynomial is a graph that is continuous. There are no breaks in the line. It starts and it goes on forever. Okay? So there are no breaks in it. It goes on for infinity. So there are a couple situations that can happen, right? When you're talking about a line, or a curve, I should say. It could start down, it could finish up, correct? That's another option. You could go up and then finish down. Any others? Or if you start up, you could finish up And there's one more scenario, which would be what? Yeah, you would start down and finish down. So you have up, up, down, down, up, down, or down, up. So those are your options. So I'll just put them over here so you can see the options real quick. Let me erase this. So there are only 4 categories. Up, up, down, 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 up, or up, down. There are only 4 different types of end behaviors. Okay? So, when you're dealing with a parabola, what do we know our end behaviors are for parabolas? They are what? What are your 2 options for parabolas? Up, up, or down, down. Those are the only 2 options. Parabolas cannot be down, up, or up, down. Now, this is a cubic, okay? We're talking about a cubic. So there are some scenarios there that can be different. Now, I'm going to work with the factored form so you guys can see it. We're going to take your factored form, and we're going to do something that's not really kosher, but we're going to do it anyway. We're going to throw infinity in there. Not the norm. All right. All right, so we're going to throw infinity in here. All right? So we're going to throw infinity into this first term. 4 times infinity minus 3. What would you get? Yeah, it'd be a positive number. So this would yield a positive number, correct? What would happen if you plug in positive infinity? To the second one, infinity plus 1 would be a positive infinity. What about the third one? A positive infinity. What is a positive times a positive times a positive? A positive. So what I'm trying to say is if this is y equals, and we have a positive infinity times a positive infinity times a positive infinity, 3 positive infinities, it would yield you a positive infinity. If y is approaching, you see this arrow? That means approaching positive infinity. Which direction is that? As we go to the right, we're going what? Up is correct. Up. All right, so let's try this with a negative sign. What happens when you throw in negative infinity? 4 times negative infinity minus 3 would give you a minus sign. Negative infinity again, a negative sign. Negative infinity again, a negative sign. Miss Murray, what happens when you multiply 3 negatives together? You get a negative. That would give me negative infinity. In which direction is negative infinity? It is down. So that is what those statements are saying. As we go right, we go up. As we go left, we go down. So I have this graph right here. What I'm saying is, as we go right, we will finish up. As we go left, we will finish down. Okay? So this is kind of the map of what we're graphing. Okay? Over here, it did talk about the y-intercept, which we already have, which was 0, 3, correct? I'm going to go ahead and plot that point. I'm going to put it right here at 3. We have negative 1. I'm going to put it over here, and 1 over here, and over here, I'm going to put 3/4. I know those are not the exact locations. I want some space so I can actually see my graph. I'm going to go ahead and label it so you can see it. Okay? Now, when I'm looking at this graph, I like to think of the axis as fences. Okay? You have 4 houses in town. They're all butted up to each other, and there's a corner fence right here. Okay? All 4 corners will meet right there. All right? So you have Alex's house right here. This is where Peyton lives. Okay? Peyton lives there. All right? And you have Carter lives here. Knox is going to live here. All right. I don't know. Liam. We'll put Liam in here. All right. So we have these 4 locations. All right. So what has to happen is we've got our arrows. Right now, at this point in time, we know that we're starting at Knox, and we want to go to Liam's house. So Knox is going to go to Liam's house. All right? Now, the only way he can get from Knox to Liam's house is go through the backyards, and he has to go through the gates. The gates happen to be our intercepts that we have, and Knox has to walk from left to right, which means that he cannot turn in on himself and zigzag or do circles or anything. Okay? So he's going to start over here at his house and start to walk towards the first gate. He's going to go through that gate. And then he's going to enter through the Y-intercept gate. Okay? Now, he has to go through every single gate before the end. All right? I know he is at Liam's house right now, but we're going to have to go through all the gates. He's got to check and lock them behind himself. So he's going to go through this one, and then he's going to turn, and he's going to walk up through this one here. And then he's at Liam's house. Okay? He has to check every single gate and go through every single gate. That's just the rule. All right? So in order for Knox to get to Liam's house, he has to go through every single gate. All right? Walking from left to right. The other rule is that he has to be chill. He's just chill, which means that there are no straight lines. So he's not going to make vertices that you would have for an absolute value. All right? He's not in the military. He's just being chill. All right? So he's not going to make some pivot turn that you guys do in band or in, all right? So it's nice, smooth curves, all right? Polynomials don't have sharp edges, all right? They don't have any breaks in the line, all right? So this is the way. Now, Knox can go a little bit higher here and then curve down. It makes no difference. Artistically, it would probably make more sense that way, but that doesn't mean that you have to draw it that way. The purple one is just as good as the blue one, okay? As long as you're touching and going through all the gates, all right, and your end behavior is correct, you're going to be in good shape, okay? And that's the way these will be graphed. This is not much different than our polynomials that we've been doing. Our quadratics that we've been doing. Okay, in our openers of last week, so they're very, very similar. So it's not a step up, right? It's kind of just steps sideways. We just add a little bit more to it. All right. So again, take a look. I'll just show you tomorrow's. That has 3 terms. So when you come in tomorrow, I'm going to have to factor that not using grouping. Here's another method. Okay? We'll go over a lot more in detail as we go along. All right. So, enough on that. Let's see if you got any questions on your homework.